experimental designs. And experimental designs are basically refined form of ANOVA that we use to test for the effect of a particular material on a particular group of people, population of things, and all of that. Now, before we go into the calculations, it is expedient that we know all of this, the terminologies, the principles, and the types of designs that we have in experimental designs. All right, so the first one is terminologies. Let's discuss the terminologies. Now, the first terminology is experimenter. Now, who is an experimenter? The experimenter is actually you, the person performing the experiment, the person apportioning a particular treatment to a subject. Now, what is a treatment? A treatment is that material, that testable material that you are applying on a subject, on an experimental unit. So, for example, you are testing for the effect of a particular drug on a population of things. So, that drug will be your treatment that you are apportioning to those subjects. Alright? Then, who is your subject or experimental unit? The experimental unit are the group of population that you are apportioning a treatment to or allocating a treatment to. So, for example, let's say you are testing for the effect of a particular drug on a population of people, even animals, say fish. So you are testing for the effect of a particular drug or feed, for example, for animals now, we usually test feed. If you are testing for the effect of a particular feed on the growth of fish, for example, then this feed will be your treatment, and this fish will be your experimental unit. Alright? The next terminology is experimental error. Now, the experimental error simply refers to those errors that cannot be controlled, that are beyond your control. They are extraneous factors that are beyond the experimenter's control. So, for example, when you apportion a treatment to more than one experimental unit, and you make sure that their system, the entire system is homogeneous, so you expect that they grow the same way. They have the same effect. But in most cases in real life experiment, we discover that even after that, making sure that there is homogeneity in the entire system, we still notice a number of differences in those experimental units. So those differences or variations are as a result of experimental errors. All right. So those are the extraneous factors that are uncontrollable. Then the last terminology here is basically the experimental design. So it's basically a refined form of ANOVA. So where we test for the variations between the mean. So you know that the mean is a central measure of central tendency that is a representative of the entire population. So that's why we're using a mean. We cannot take one of the outcomes. So we use a mean. We take a mean, but the mean of the entire population, which is a good representative of the entire population, and then compare these means and see the differences or variations. Alright. So now let's go to the principles. The principles of ANOVA. Now, what are the principles of ANOVA? The principle number one, there are three basic principles of ANOVA. We have randomization. Number two is replication. And number three is control or local control. Alright? Now in randomization, very simple. Randomization simply means the apportioning of treatment without bias. That is making sure that the probability of every experimental unit getting that treatment is the same. So that is randomization, making sure that you apportion treatment without bias. Alright? Then replication simply means that apportioning treatment to more than one experimental unit because of errors and to increase your precision. This replication increases precision. So because if we apportion treatment to only one experimental unit, it is possible that the outcome does not, that outcome is not good enough to represent an entire population. So we have to replicate that treatment for different experimental units. Alright, then the local control simply means, for example, in medicine, we use what is called, if we are testing for a drug, we use what is called a placebo on treatment, on patients, to make them feel like this drug is what they are using. That placebo will be told to them as if it was the drug actually that they are testing for. That control is to put a standard in place that has been what we know as the normal. So to see what deviation this drug will have from that normal, what effect that it will have, what variation it will have over that normal. So that normal is the control. So in a system where we have, for example, a group of maybe influential people that earn high income, they tend to behave in a specific type of way. So we segregate them, put them together. A system where we have people that are average earners, we put them together, and people that are low level, we put them together. So that system is called blocking and balancing, just to make sure that there is no bias when we apportion treatment. So that is called local control. Alright, then let's go to the designs, the types of designs that we have. The types of designs that we have are the CRD, the RCBD or RBD, and the LSD. Alright, so there are basically more designs, but these are the major 3 designs that we use in ANOVA. Okay, so CRD stands for completely randomized design, RCBD stands for randomized complete block design, and LSD stands for Latin square design. Okay, so let's discuss the designs separately now. First, we are going to be discussing the completely randomized design. The first type of design we are going to be considering is the completely randomized design. Now, the name stems from the way the design is in terms of structure and form, and in the methodology of adopted in solving the question. All right. Number one is it is completely randomized because what that means is that the treatments are being apportioned randomly at random. That is, there is no bias in the allocation of the treatment to the experimental unit. It means that each experimental unit, regardless of their number, have the same or almost the same probability, in fact the same, not almost the same, it has the same probability of getting a treatment. All experimental units, they have the same probability of having this, getting a treatment. So for example, if I use about 5 feeds in about 20 pounds, or I use like 7 feeds in like 49 pounds, the 49 the 49 points will get seven treatments will be allotted to those for each of 7 points there, so that like every of the points there will be allotted each treatment 7 times. All right. So for an example like this, you are going to see this. We have that hybrid catfish from 4 different sources are being compared in order to select the best source from which seeds could be procured for distribution to the farmers in Lagos. The 4 sources are Ile-Ife, Ibadan, London, and Zaria. After stocking in a pond in Lagos, the same rearing conditions were carried out on them, and the following yield in weight was obtained. The following yield, okay, that is this, the whole table was obtained. All right. So in this table we have Ibadan with this weight yield, and this is Ile-Ife, this is Ibadan, this is Zaria, and this is Lagos, London rather, London. So there are there are four sources of variation, right? So the basic idea in CRD is that our variation come from two sources. Our variation come from two major sources, right? And remember that we said that variability in total, that is the total difference that can occur in our experiment. Step comes from the variability in the treatment, or variability as a result of treatment, and the variability as a result of extraneous factors. These extraneous factors are the factors that are beyond our control. Now let me explain. Having subjected, listen to this word, this expression here. It says that they were subjected to the same rearing conditions. So now, if it was not a real life situation, you subject the same subject or the same experimental unit to the same condition, homogeneous condition. You make sure that there was high degree of homogeneity in whatever you subjected each of the group to. We expect the same result. As in, for example, in yield of fish, if we subject them, if for example, if it wasn't a real life case, like ideally, which is not in real life. So ideally, if I subject those fish to the same condition, let's say their weight should be, the outcome of whatever I get should be the same for everything. So in that case, there will be no variability and will not be testing for variability. So for example, if I subject them to the same condition, I could have, for example, the outcome of the weight, I could have like 5, 5, 5, and 5 all through. I could have like 5, 5, 5, 5 all through, 5, 5, 5, 5 all through. Since I subjected them to the same condition, for example. Alright, so but because we are changing we are altering a particular condition. For example, it could be that we are altering maybe we are altering one of the components, like the feed we are feeding to those experimental units. Then it means we have by ourselves introduced a source of variance. But ideally, if we did not put any source of variance, what we should get should be all of this equally. And all of those formulas that we apply should give us no difference. For example, when we calculate correction factor, then we have to subtract from sum of squares total and the rest that do. Everything should amount to 0 because there should be no variability. Of course, correction factor minus that SSR should give us 0. The treatment minus the sum of square treatment minus the correction factor should also give us 0. Why? Because there will be no variability. But by ourselves, we introduce the variation by changing or altering one of the components. For example, we set this first group a particular A diet, we set the second group a particular B diet, and we set the third group a particular C diet. Now this is a variation, so of course we expect that there is a degree of variation in the outcome of the result. So what we are now testing for is this variation. Now, and this variation is, now these are the factors that we can control. So this variation can also come from factors that we cannot control. For example, humans or maybe even the fish, they have certain intrinsic factors that are beyond our own control. So those might also play out in the outcome of the experiments. So for example, if I have a man A and I feed them for 5 days with the same diet and the rest, or I said 5 days, 5 years with the same diet and the rest, in that 5 years they cannot grow to become alike. They will vary in different there are some other conditions that will vary in them. Of course, they might look beautiful, almost equally grow tall, almost equally, and the rest of that. But there will be certain differences because of their genetic makeup, for example. So a genetic makeup, for example, genetic makeup is one of the extraneous factor. It's one of the extraneous factor, and it's this extraneous factor that is being accounted for in the error. So all those errors that we always calculate, sum of squares error, is as a result of extraneous factors that are not controllable by the experiment, by the experimenter. But the experimenter can actually control one other factor, which is the treatment that is allocating to the experimental unit. Now, after allocating this treatment, what we now want to check is that if we already know that there is going to be variability because of the difference in treatment, in this treatment, because we know there is going to be a variability, and we already know that there is going to be a variability because of error, so giving us a total amount of variability. But we want to now check that the variability in this treatment and the variability in error, if we compare these differences, is it enough to say that, oh, this this treatment actually was effective? That can we surmise that the variability was actually largely due to the effect of the treatment? So, for example, if you produce a variability value, when you compare, for example, you have treatment and you have a variability value of around 5, and you compare and you get for your error, you got a variability value of like 2, for example. You see that when you divide this is going to give you what? 2.5. Now, if you compare this with your statistics, the F distribution table, and you see a particular F value that is less than this, it means that effect, this is our MS treatment and MS error now, for example, MS treatment, MS error. Now, it means that this treatment has produced largely enough effect, has had a more obvious effect on our subject, our experimental unit, more than the extraneous factor, more than the error within that cannot be controlled. So that is why we do all of the calculations that we have to do. That we want to test that is the effect due to treatment significant enough to be able to say that, hey, this variation was actually due to the effect of the treatment, and how do we test that? It must be very, very much greater than the error, so that when the error divides it, or when we compare, because it's actually a comparison, when we compare with the error, it's going to give us a value that is greater than the F tabulated value, and then we can summarize that, oh, this effect was due to the treatment error. Alright, so we are going to be solving this question. Now, there are a number of steps that we have to follow ideally. Now, it depends on what you are actually using this for. So, for example, if you are in fisheries department or FUTA, you have to follow a number of steps to solving a question like this. All right. So the solution. All right. So the first thing that we have to do is to tell the name of the design. We'll write the name of the type of design. So seeing this, you will notice that the only source of variation here are the points or the sources of those fish, or those tilapia is the same string. So those fish, which are Inefe, Badon, and London and Zaria. So that's the only source of variation. We did not apportion different feed. In fact, we fed them with the same feed, we put them in the same kind of pond, and the rest of that. But the only difference is the fact that they come from different sources. So, and that is the only thing we are testing for. So that is a completely randomized design, because it is only one source of variation that we have. It is also called a one-way ANOVA. In fact, that is the reason why it is called a one-way ANOVA. Alright, so I said the steps that will follow in solving this kind of question. The first one is that we name the design. We name the design. And what is the name of the design? A completely randomized design. Alright. Now don't abbreviate. At the end of the day, you can abbreviate, but don't abbreviate. Don't just write CRV. You write it in full. Now the number 2 step is that you write the model. Now the model of this design, which is the CRD design, is Yij equal to mu plus the treatment, which is tau I plus the error ij. Right? This is the model of the CRD. The model of the CRD. And what it's just saying is basically that when we are looking for a particular Yij value, any of this value here, it is simply a sum of the mean, of the grand mean, and the treatment, error due to treatment, and variance due to treatment, or effect of treatment, and the error within. So a sum of this is going to give us the actual value of any of the item we are looking for, either on this row or this column. You know, the I and J represent the row in which it is found. So the particular Y in the particular row and under a particular treatment. Alright. So the next thing that we are going to find, we are going to do, which is the third step, is to state our hypothesis. So we write hypothesis statement. Now, this is one of the most important steps that you cannot even skip, because what we are actually testing for is this hypothesis. So we want to know we have to state the hypothesis. We want to know what is the effect of this variation. Alright, so then there are 2 types of hypotheses. We have the null hypothesis and the alternative hypothesis. Null hypothesis, this is the null hypothesis, and the alternative hypothesis, or you can see it written as H1, alright, H sub A or H naught, or H1 rather. Then this is the alternative hypothesis. Alright, so, and you make sure that when you want to answer the question, you tailor this your hypothesis down to meet the question, to meet what the question requires. Alright, so our null hypothesis, basically our null hypothesis is an hypothesis that says that there is no difference there's no significant difference in whatever treatment you are talking about there, and the alternative hypothesis is one that says that there is significant difference. So, but usually there are 2 ways of stating this. Since we are comparing the means of this thing, you can just simply say that the null hypothesis states that there is no difference, no significant difference between the mean, the mean rather, the ground mean of all the treatments. In this case, there are 3 treatments or 4 treatments. So mu1 is equal to mu2 is equal to mu3 is equal to mu4. But if you want to state that in words, in sentence, you can say that there is no significant difference between the yield of the 4 sources, between the yield of fish from all 4 sources. So we say that there is no, this is the major term there, there is no significant difference between the yield of fish from all 4 sources. And the second one is that it does the opposite, that there is significant difference between the yield of the fish from the 4 sources. All right. So that is our hypothesis statement. Now, the step 4. So please don't miss the steps. The step 4 is we now present a proper layout of this table. A proper layout. Now, because with the way this table is given to us, it is scattered. So what we basically do is we now separate all of these different treatments. We now separate them into different columns. All right. So for example, we are going to start with I, B, Z, and L like that, in that order. So we have I, which is the Ile-Ife strain, the Ibadan strain, and the Zaria strain, and the London strain, and okay, so I guess there are 4 strains like that: Ile-Ife, Ibadan, Zaria, and London, and Zaria, I guess. So those are the 4 strains. So we now separate them like this. All right. So for Ibadan, we have 17.01. Now, I'm going to tell you how to recognize that this is a CRD design. Another way to recognize. So we have Ile-Ife. This is also Ile-Ife 16.57, 16.60, and 19.54, and 16.60. That is Ile-Ife. Then we go here 15.82, and the last one 16.34. So that's the last yield from Ile-Ife. The next one is Ibadan. We have 19.86. We have 19.54. We have 22.58. We have 17.67. We have 17.43. Then the Zaria strain, we have 16.22. We have 21.30. We have the Zaria strain, here, 20.84, 19.27, 14.80. Alright, and the last one is the London strain, the 20.34. We have 20.34. We also have 21.24. We have 25.05. We have 21.29, and we have 19.43. All right. So now, how do you recognize? So we have presented a proper layout of the table. How do you now identify that this is a CRD? Number one is that this arrangement tells you that it's a CRD. Why? Because it is only one source of variation that you have. These are the only things that vary here. There is no blocking or no other treatment being applied. So you see that since there is no blocking or no other treatment being applied, you know that this is CRD because there is only one source of variation, which we consider as the treatment in this case. All right. So the next thing we are going to do is compute. So the computation is going to happen here. The computation is going to happen here. But what I'm going to basically show you is the steps before we compute. We have to first find the total of all of this, the total of each of the treatments. So we have to find the total of the treatments total. All right. I'll put them here. And of course, because there is a possibility that there is a significant difference, we should also find their means, so that when we want to do a post hoc test, or a follow-up test. A follow-up test is a test that we use to confirm where that source of variation actually lies. I mean, which one is actually significantly different among these treatments. So we need to find their mean as well. All right. So we find their means. Okay, so now let's calculate the grand total of each case. So these are the sum of treatments. So these are the total sum of treatment for this one. For the elephant, we have 82.34, we have 97.08, and 92.43, and 107.35 for the last one. Then we now computed their means. And how did I get the mean? Simply the summation of this over how many replicates we have here. We have 1, 2, 3, 4, 5. So this divided by 5, this divided by 5, this divided by 5, this divided by 5. I divided by 5 all through because the replicates are homogeneous. So it is the same for everything. So these are the means. Alright, so let's go to the actual computations. The first thing we are going to be calculating for is the correction factor. And the correction factor is given by grand total all squared over n, total number. So that will be, the grand total is simply the summation of all of this over n. N is how many items we have here. And how many items we have here? 1, 2, 3, 4 times 5. 1, 2, 3, 4, 5, that is 20. So we have something over 20. I'm going to compute that now. Alright, so I calculated the grand total and I got 379.2, and I plugged it in and squared it. After squaring it, I divided by 20, which is the total number of results we have there, which is 20. So we have after squaring this, I have 143,792.64 and divided by 20, and I got this. So these are correction factor. Alright, so the next thing we're going to do is that we're going to be solving for the sum of squares total. So we have started to check for the variations now. So the sum of squares total is given by the formula summation, and then there are two possible formulas. It's either you take, so using y, we can say that is the summation of all y values minus summation of the square of all y values. So minus correction factor. Let me explain what this means. This means that we are going to square each of these items. Square each of the items, square each of the items, square each of the item, and we'll be subtracting this correction factor from the sum of everything. So after squaring each one, we add up everything and we'll subtract from CF. I will subtract CF from it. So we have 17.01 all squared plus 16.57 all squared plus 16.60 all squared plus 15.82 all squared plus plus the last one. Now, in order to conserve space and time, this is the best way to do it. So what you will now do is, when you want to punch your calculator, punch for 1, 2, 3, 4 or so, and punch for this last one, and you are going to also put this ellipsis to show that, you put the ellipsis to show that it is for all of the items there. Alright, just to minimize your work. Alright. So we have squared this and squared this and squared this and squared this and squared this. All we have this and this and this and this plus this minus the correction factor. Alright, so at the end of the day, by the time you sum up all of this and you subtract the correction factor from it, you are going to, by the time you sum up everything and subtract the correction factor from it, you are going to get an SS total value, SS total of 133.83. Alright, 133.83. Then the next thing you calculate is your SS treatment. So notice, you calculate SS total first, then SS treatment. Now, SS treatment is given by the formula summation of all our treatments squared. So we are squaring all our treatments total. So it's actually that we are squaring all our treatments, the tau I, tau, something like this. So we are squaring each one, the summation of our treatments. We are squaring it. So we are squaring the summation of our treatment, and so for each of our treatments, we are going to square the summation and then divide by the replicate. Then we'll subtract the correction factor as well. So it means we are going to square this 82.34 all squared plus 97.08 all squared plus 92.43 all squared plus 107 rather 0.43 all squared. Now all over 5. Now the reason why we are using over 5 is because everything have homogeneous replicate, 5 in each case. If the replicates are unequal, as we see in other example, we are going to divide each one by its own replicates, Let's say this were to be 2, we're going to say 82.8 squared divided by 2. If this were to be like 4, we say 97.08 squared over 4, and like that, and we'll divide each case before we subtract I will subtract the correction factor from it. Remember, our correction factor is this. So by the end of the day, after calculating and subtracting the correction factor, we should arrive at a correction at an SS treatment of 64.71. So this should be the correction factor that we should come up with. Alright, so we are going to do the other 2 steps. So what we want to do basically in the remaining 2 steps are to calculate we've done the SS total, the SS treatment, then the next will be the SS error. Alright, remember in the beginning, we can just put SS sub ERR. Alright. Remember in the beginning, we said that the total sum of variability is actually equal to the sum of variability due to treatment plus the sum of variability due to error that is beyond our control. Okay, so the way we can solve for this error is simply by making, since we have solved for SS total and solved for SS treatment, let's simply make SS error subject to formula, and that becomes SS total minus SS treatment. Alright, so that's what we're going to be doing now. We'll simply be subtracting the SS treatment from the SS total, because SS total minus SS treatment, right? So SS error will basically be equal to our SS total gave 133.83 and our SS treatment gave 64 minus 64.71. So and the answer that is going to give us for SS error is going to be 69.12. 69.12. Alright, so these are our SS error. Alright, the next thing we are going to now calculate for are our degrees of freedom. Our degrees of freedom, DF. Now we start with the DF total. So the DF total is basically the total n minus 1, and our n in this case is 20. That is the total sum of total number of yield or result that we have. That is 20 minus 1, and that becomes 19. Now the next is the DF error, the DF treatment rather. We always calculate total first, treatment, just do we did that, total treatment error. So we are doing DF treatment, DF error, and alright, those are the 3 we are calculating. So for the DF treatment, how many treatments do we have? We have 1, 2, 3, 4 treatments. So we have T minus 1, that is 4 minus 1, which is equal to 3. And for the error, we are going to subtract DF total the same way we did this. We subtract DF treatment from DF total. Alright, so that becomes 19 minus 3, and that is 16. Alright, so those are our DF values. And the last step is to calculate our MS, which is mean squares. Our mean squares. So our mean squared. Now we have succeeded in solving the entire question in order to reduce the time of the longevity of the video. So MS treatment is basically SS treatment over DF treatment. And you know that our SS treatment was 64.3.71 over 3, which is DF treatment. And we got this. Then the MS error was SS error. We'll just divide the sum of squares by the degree of freedom. That's the formula. So SS error over DF error, the concomitant or corresponding degree of freedom. So 69.12 divided by 16. Alright, so we have our MS error to be 4.32. So the next thing we now do is we take the variance ratio. That is, we relate both of those MS values to know how far from each other they are, how the relationship between them, their ratio. So that is what we call the F cal, the F sub cal. That is F calculated value of our F distribution. So this is going to be the answer. If you relate both 21.57 by 4.32, you get 4.97. Alright, so having done all of this, so that's the last step for the computation. Now, we will now prepare an ANOVA table. An ANOVA table. So, now this is the layout of our ANOVA table. You have the source of variance, and the source of variance are our treatment and our errors. So then the next you have is your DF, your degrees of freedom. You have we have plugged everything in 3 and 16 and 9 and 19. The next one is your sum of squares. Our sum of squares, I put them in and the total, and then the MS. The one we calculated here, 21.57, 4.32, and of course I've told you that we don't need the total. So then our F cal is 4.97. So the last part is to now check your F distribution for your F tabulated, your tabulated F value. So what you will do is go to an F distribution, and I'm going to show you what to do. Your vertical column is the error. So always check the error in the vertical column and the treatment in the horizontal row. All right. So what we are going to do is our alpha is 0.05. That's our p value. So we are checking it under a probability value of 5%. That's what it means. All right. So under the probability value of 5%, I hope this is quite clear. You are going to go to you check here for the error. Our error is 16 and our treatment is 3. So we are checking for 16 under 3. We are checking for 16 under 3, error 16. So we go down like this and we'll go to 16. So this is 16 here. So we check for 16 under 3. This is 3 here. This is 3. So we check for 16 under 3. So this is 16, and we trace to that 3, and we have 3.24. 3.24, if I am very correct. We have 16 under 3, so that's 3.24, and that is going to be our F tabulated. So 3.24. All right. So then we will now compare both values. So since our F cal is now greater than our F tab, of course 4.97 is greater than 3.24. What do we do? Since it means that there is a significant relationship between them, that is a significant difference between them, that is F cal, what we calculated, is actually greater than what we were expecting. So since it's greater than what we are expecting, then it means that the effect of the treatment is actually significantly different. So it means that we accept the alternative hypothesis, because that's the hypothesis of significant difference. So it means that we accept, so you now write conclusion, we accept, you say since F cal is greater than F tab, we accept the alternative hypothesis, that is the HA, and reject, you can continue further by saying, and reject the null hypothesis. Of course, we have accepted one, we have rejected the other. Alright, so since we have not accepted the alternative hypothesis, to check where the source of, which one is actually specifically significant difference, we will now have to carry out a post hoc test. And for the post hoc test, because of the longevity of the duration of this video, we already cannot do it now. So we are going to use the second video to carry out a post hoc test on this question and get which of the means is actually significantly different. Thank you very much for staying to the end. Please do also subscribe to the channel. God bless you.